Yeah, hello everyone. My name is Peng. I'm an engineer manager in Uber AI platform, also known as a Michelangelo team. And this is Bharat.
Hi everyone. My name is Bharat. I'm an engineer on the ML training platform at Uber.
Yeah. So today we are going to talk about how we use Ray to, train our model, especially on our journey of like increase the model size and how to train the large models. So Michelangelo is actually a centralized platform that a lot of Uber's application cases is trained on top of it and serve on top of it, including the rides, eats, for example, the destination search, the ETA estimation, the dynamic pricing, fraud detection, personalization feeds on your restaurant, like semantic search, ranking, manual contacts, promotions, also have some models behind the scene like customer support, all those things. So it's like a centralized platform, and all the production teams are using our platform to train their models. Our mission is basically trying to scale up their model, trying to scale up their data, and try to train their model reliably and efficiently. So this is our training framework and dependencies. So in the bottom layer, we have data layer and the compute layer. Data layer basically using HDFS on-prem, and also we use CFS on cloud. On compute layer, we basically use Kubernetes. On top of that, there's a distributed training layer. Basically, we use Ray, which is like the central module of the entire tech stack. And on top of that, we have all the deep learning frameworks like PyTorch, TensorFlow, along with those distributed training accelerators like DeepSpeed, Harvard. We also use DDP, which is part of the PyTorch. And also we use CUDA for the NVIDIA hardwares. This is kind of like our journey on core ML, because I think 2 years ago we already shared our fine-tuning framework for large language models. So this time we will focus on the core ML. So for core ML, you can see our model size is becoming larger and larger through the years. And basically we evolve from data parallelism to model parallelism, or like zero from the DeepSpeed. And we also evolve our framework from TensorFlow, PyML to PyTorch, and we also onboard Ray, which we use Ray to scale up all our data and the model in different clusters and cloud providers. And starting from this year, our core ML models starting to be larger than the GPU memory limitations, so we need to do a model parallelism on top. We also do incremental training because the training time is longer. We want to train it incrementally. We also have a lot of optimizations on top to improve the efficiency. For people who do not know what is the DeepSpeed, basically is called the zero redundancy optimizer. It's actually shard, like on top of the data parallelism, it's actually shard your model parameters, your gradient and the optimizer states, and only put a part of the model shard to each GPUs. So by doing this, you can reduce the memory redundancy across different GPUs and allow this entire cluster to train a much larger model than a single GPU memory can hold. It's by the way, it's very similar to PyTorch FSDP. If you see like those terms, they are actually using the same background implementation. On top of DeepSpeed, we also do a lot of optimizations, which we discovered the needs when we change our model size up. For compute layer, we do first we upgrade the hardware. from our legacy hardware, which is RTX 5000 based, very similar to L4. And we upgrade that to A100 and H100, which unlock a lot of advanced features like low precision training, and also it can help us to improve the overall efficiency. And second, we optimize our job provisioning strategy. So we kind of like pack our instance inside one host before we scale out to multiple hosts. That is because inside a host, GPUs communicate by NVLink, which is a very high bandwidth. And across different hosts, it's actually used the networking, which is much slower than the NVLink. So by doing this strategy, we see a lot of improvement. And also later this year, we onboarded the B200 GPUs, and we also enabled RDMA on top, which gave you a direct communication between GPUs across node. Can improve further for this cross-node communication. On the framework layer, we mainly do three things while we will scale the model size up. First, we need to deal with the embedding layers. We use multi-hash embedding, which basically reduce the embedding lookup time without like compromise model accuracy. The second, we do the mixed precision training. It's actually put most of the computations into lower precision tensors. By doing that, we can accelerate the overall training speed. We didn't put everything in low precision because we think the mixed precision strategy can benefit from the numerical stability of the entire system. Lastly, we do flash attention. It's kind of like a kernel fusion optimization. So the GPU card, it has an on-chip high-speed memory called SRAM. It's super small but fast. It also has HBM, which is like the GPU memory in general. Usually, your model weights are and the optimizer state is hosted in the HBM. And whenever you want to do some calculation, you first copy the tensors from the HBM to SRAM, and then do the calculation. And then you copy back from the SRAM to HBM for your next step. So the idea of the flash attention is basically you fuse all the operations inside one kernel. So you do not need to copy back and forth between your on-chip SRAM and the HBM. By doing this, you save a lot of time on the memory copy and improve the overall efficiency. So by combination of the compute layer improvement and the framework layer improvement, we achieve like 10 times throughput on top of the hardware we upgrade. And the key learning for us is like the scaling law highlights the needs of this model platform hardware vertical optimizations. So you need to find the way wherever you can do to optimize the system. It's not limited to modelers' work. It's also like a lot of infrastructure work along with those hardwares. For next, I will talk about our resetup. Before that, I want to briefly give you an idea about our scale on our read jobs. So we have about like 2K read pipelines running per day. 60% of them are like GPU related work. We also have a read job on IC Boost, which running on CPU. And for the GPU jobs, in average, it's about like 3 hours per job. We have like a P90 about 5 hours and P99 like more than 1 day. So this is basically the scale and the challenge we want to solve. And we also, from 2 years ago, we start to move ourselves from on-prem data center to cloud. And right now we need this like a global routing strategy, which means we need to first check if the data is synchronized in between on-prem data center and cloud vendors. And then only the data is available on the destination. Then we start schedule the GPU jobs. We also think about doing expand this to multiple cloud vendors and also build a result availability APIs on top. And this is kind of like what our pipeline look like. So we have upstreams. Usually it's like those data pipelines. They generate the tables for us to consume. And we first run some data processing job. It's either in Spark or on Ray to consume those tables, like join multiple tables, do the feature engineering on top, and then dump some Parquet files. And then we save those Parquet files in a file system, and then we can distribute that to a different cloud vendors, and use the hardware in different clouds to train those models. And for the GPU job, we mainly use Ray on top of Kubernetes. So this is the benefit that Ray can bring to us, because Ray and the Kubernetes is kind of like a general across different cloud providers, so which keep us simple in our tech stack. We do not need to worry too much about integrate with different cloud vendors. As long as they can support Ray and Kubernetes, our job controller can launch job to them. And then when GPU job finish training, we copy the model and metrics back for our downstream to consume. And it can be some evaluation work, it can be some scoring work or batch prediction work, to generate models offline. And also it can deploy to our online service to serve the model online. Now I hand over to Bharat, who will talk about the details on how we launch Ray jobs.
Hi everyone. So now we'll go a bit deeper into how our Ray-related infra is set up, right? So this slide shows you an overall of how our architecture is set up. So we have like this layered architecture. At the top layer, we have all of our user clients. So basically there are CLIs, there are notebooks, and there are other kind of frameworks, custom in-house framework that we built in-house, right? So those are kind of the clients of our Uber AI platform. And then the middle layer shows the actual platform that is exposed to the user. So our platform is essentially modeled based on Kubernetes-based reconcilers. So essentially what we have is that we have two services. One is an API server and one is a controller manager. And the API server essentially on the left exposes gRPC-based APIs for the clients to consume. And then and what we've done is that we've modeled a whole lot of artifacts related to our pipeline processing as what's called CRDs, which is custom resource definitions in Kubernetes. And so the idea is that our clients can use native Kubernetes APIs to work with our control plane that we expose. And so Ray job is also modeled as a CRD, which is then kind of washed by this job controller on the right. And the job controller has kind of two components to it. There's a scheduler and there's a controller, right? And so essentially what we try to do here is that actually let me skip over a bit to our bottommost layer first. So Uber today has a presence in or does data processing or machine learning on both our own data centers as well as on cloud. So essentially we have a mix of data centers as well as cloud that we work on top of, right? So it's very important for us to provide federation of resources so that our users do not have to worry about what resources and what cluster this job is going to run in, right? So from their perspective, they just say, hey, this is a job I want to run, this is the data, go figure out where to run it, right? So that's kind of the idea of providing a federation. And so what we do is that we basically model these underlying clusters also as CRDs, which are cluster CRDs, and we do all kinds of things like secret management and cluster management, etc. For them. And so the idea is that the scheduler, when it sees a job, is able to find a cluster that is suitable to run that job, right? And it can depend on various affinities, like say I want to use a GPU, I want to use a certain type of GPU SKU, I want certain type of memory, certain hardware, and so on. So that's how our architecture is set up. And then we also, and then this diagram kind of shows how a job life cycle kind of looks like. So on the very left, we have a user, right, and which essentially makes a request to the API server, and then before like before we talked about the job scheduler picking it up. So actually, the job scheduler is then modeled as a job queue, which is something that we talk about later in our resource management section. But the idea is that we have some very clear interfaces between the controller and the scheduler. So the controller will ask the scheduler to or will essentially queue a job to be scheduled. From there on, the scheduler will pick it up and assign a cluster to it, and then hand the control back to the controller, which will then monitor, which will then launch the job and monitor its life cycle. And later on, we'll talk a bit more about what monitoring lifecycle, etc., means, right? So one of the aspects that it implies is that this kind of layer acts also as things like retries and error handling. So for example, if something goes wrong, we can transparently move the job somewhere else. And we have another kind of component called cluster controller, which is essentially the thing or the controller that monitors the health of the underlying cluster. So for example, say a cluster is down because of some maintenance or some kind of platform level upgrade like kubelet maintenance or host upgrades and stuff like that, right? So his job is to kind of keep a tab or keep an eye on what is the health status of each of the underlying resources and the clusters, and it provides that as a near real-time snapshot to the scheduler. So think of it as a consumer and a producer kind of a thing where the cluster controller is providing a snapshot of the resources available to the scheduler, and then scheduler is the consumer, which then assigns the job appropriately, right? And then our scheduler is also organizational aware, right? So essentially, like any other mid-sized companies, Uber has this organizational hierarchy, and each organization would typically have their own budget, using which they can procure some resources and so on, right? So what we do is that we kind of honor the policies that are able to understand pool level ownership. So for example, we are able to determine who the job belongs to and who the resources belong to, and then route the jobs appropriately. And then we have some kind of policies that also try to match jobs depending on like the organization level, the team level, and so on. We also provide some flexibility on how teams can collaborate and so on. So there's a very rich ecosystems of the policies that can be seamlessly make resources available within Uber. Then here we talk a bit more about lifecycle management. In particular, we talk about how we kind of manage the job history, right? Because like from a user perspective, like a job is done, but from a platform perspective, we want to make sure that we track the job history. So for things like auditing, things like debugging, and things like event states, right? So even if like a job has succeeded, we may want to look at what happened to how the job transitioned through various states days after, right? And so for that purpose, we don't actually delete the CREs. What we do is that we have a way to mark them as immutable, and so there is essentially no hard deletes. So what we do is that we basically say, okay, once the job is done, we mark it as immutable so that it's still available for auditing and debugging, but then we move it out to an external storage so that they are there and indexed forever for us to be able to debug and audit and all those things. So for that, we have built this custom termination protocol, wherein a client can go and initiate a termination. So for example, a user can say, hey, this run is taking too long and I want to try something else, and I don't want my resources to be held up, right? So they have the ability to be able to kind of go and initiate termination on a job, and then our controller kind of takes care of the entire workflow where it is able to propagate the termination all the way to where the jobs are running, and then kill the pods, and then provide the status back to the client. One more thing to be kind of aware is that our clusters are we support multi-tenancies, and essentially clusters share hosts. And the other thing is that we at Uber have this concept of dynamic ports. So to provide full flexibility, we actually try not to use static ports within our application, and so we have this concept of being able to generate ports dynamically. And so what we do for that, and in that scenario, you can imagine that the client would need to kind of discover wherever their array cluster is running to be able to then connect to it and execute on it, right? So we have this kind of custom discovery protocol wherein the array operator, once it launches the job, it kind of keeps a tab on the pods that are coming up. And once the pods have come up, then it is able, it knows what the IPN port that the various ports have come up on, and it exposes that information back on the CRD, which is then available for the client to consume, right? Just to note that the ray operator that we mentioned here is our global control plane. This is not the kube ray operator, right? This operator has the job of managing the job lifecycle from a user perspective and provide federation. To actually run the job, when we submit the job, we use the kube ray operator, which is represented here as the local ray operator. And so the kube ray operator is the one that is responsible for actually spinning up the actual ray pods, right, where your custom logic runs. And we have found that this is quite a bit of an extensible paradigm. So for example, we are able to expose other services like Jupyter Notebook, dashboards, and various other things. And so once we are able to run them, we can use the same discovery mechanism to expose various ports on the ray cluster itself. So so imagine the scenario like you want to have a seamless experimentation to a production kind of experience, right? So what we allow users to do is that we allow them to spin up a ray cluster, and we directly are able to run a notebook inside the ray cluster, and then then expose that as a service to the user. So this discovery mechanism is used for that. One other thing I want to point out is that as you can imagine, this is a multi-layered and kind of a complex stack. And our users are essentially machine learning engineers and data scientists who are not the experts in this tech stack, right? So and we've seen, like in several other talks and talking to folks, that our end users may essentially find it hard to debug any errors or any issues with the stack, right? So what we've done is that we've come up with this mechanism wherein the job controller actually monitors the life cycle, and so it's actually able to monitor that if there was an error, what the error was. So for example, we are able to detect some basic things, like for example, hey, the scheduler did not provision the pod, or some container did not come up, or some of the common errors like right? Because when an actually happens, then the container's exit code will actually show that there's an and so we are able to monitor that and propagate all of that back to the user. So that helps in pretty fast iteration, from the customer perspective, because they don't have to debug anything of that sort. They just know right away what the error is, and then they can iterate on it. I'll talk a bit more about how the resource management works. So I alluded earlier, that our resources are essentially organized into pools that are arranged hierarchically, right? And this is what the scheduler refers to when it makes organizational aware scheduling. So you can think of this like a big tree where the nodes are the actual resource pools, and every pool could be owned by a team, and eventually sub teams form an organization, and so on. So what we also want to do is that when some of the teams are not using their resource fully, then we do not want those resources to go waste. We instead want to allocate those resources to some of the other teams that are already over their budget and their resource capacity. And we are able to do that seamlessly while still maintaining the fact that we are doing organizational aware scheduling. And this is called elastic resource sharing. This is something, by the way, which is already open source. Before Kubernetes, we used to use a different job scheduler called Peloton, and so I have a link here, and essentially this is all open source already. So when we moved to Ray and therefore to Kubernetes, what we did is that we ported this dynamic scheduling to Kubernetes, because Kubernetes does not natively come with these features. And so again, like going back to kind of making sure that everything is native, these resource pools are also modeled as CRDs. And these resource pool essentially monitors all the pod events to track the demand and the usage, right? So demand is essentially the set of jobs that are not able to run and essentially are waiting, right? And so what we do is that based on the demand and the current usage, we calculate this thing called an entitlement, right? So what entitlement means is that I have too many pods waiting, and so so we try to gradually provide more and more entitlement to that pool so that it can accept more borrowed capacity from other pools. And so we have a custom admission controller based on this entitlement concept. Yeah, this is more or less our presentation. By the way, my client law is being open source. We are offering early access to a few adopters, and so if you're interested in any of this stuff, we are happy to hear from you and collaborate with you. And these are some of the blogs that we have published before, and they have more details on the material that we presented here. Yeah, thank you.
All right. Yeah, so we still have 5 minutes.
Yeah,
we can take some
questions. Yeah, yeah. I don't know if there's a mic. I don't know what the protocol is. I don't know if you're supposed to take a mic or.
Yeah,
sure. Yeah.
So Kubernetes keeps moving around containers, and so how do you handle long-running jobs being stopped in the middle and moved around and stuff like that?
So Kubernetes would not necessarily move the containers on their own unless they are preempted because of some reason, right? And so preemption can happen because we have a custom, resource manager, which kind of maintains policies at a per pool level, right? So for example, say I'm running on borrow resources, but then the other party that actually owned the resources want the resources back, right? That is one scenario where the jobs would get preempted. But then what we do is that we are able to monitor, like I said, like the job controller is able to monitor that this job was preempted and provide that signal all the way back to the user. So then the user knows that, hey, right now, whatever workload you want to run, we do not have capacity for it, right? And Uber as a company, like the scale and the size we are at, we are very careful about making sure that our resource efficiency or resource utilization is very high, right? So you do not always have infinite resources available to you, but we try to essentially make the most of what we have. So yeah, I hope.
I think we do have priorities on
Yeah.
those jobs.
Yeah.
Those not tied to the length of the jobs, but more of like is a production job or versus dev job. So during preemption, we usually terminate the dev job first and keep production job running.
A follow-up question. Does they do any retries, fault tolerance, like if it's a worker faults were preempted or something?
I don't think we rely on Ray to do those things, but I know Ray, any skill system, I think, have some implementation for fault tolerance and middle epoch checkpointing and the resume. But we're planning to experiment on that, but we are not fully use that yet. Yeah.
Yeah, I have a question. So you mentioned the multi-cloud, basically reclass provisioning different cloud. Is there any kind of data dependency for storage of like a certain cloud provider storage? For example, if they file from S3 or GCP to cloud store, is that part of the scheduling or is schedule taken into consideration?
Yeah, I think.
Yeah, I think I can move to that slide. I think we had a slide on this, right? So.
Yes.
This one. Yeah.
Okay, so we are using Ray data to do the data loading to load our Parquet file. And you are right, the different cloud provider have different storage. But I think Ray data is compatible with different cloud providers. For example, S-Ray, GCP, they have special plugins underneath. So the user's code is the same. It's what's underneath inside Docker makes the difference.
So you guys take care of which provider the compute?
Yeah. So.
Yeah.
So essentially, like we are able to, like during part of scheduling, we are able to figure out like how to co-locate the data and the GPUs or the resources compute, right? Yeah. So we take care of the data movement, and then we are also working with the data team inside Uber to provide more seamless technologies which can do like remote reads and so on.
Yeah. So there is a HDFS lab layer that our data team provide that can dynamically work on both on-prem data center and cloud providers. Yeah, so our code doesn't need to worry about that. And also synchronization, we call the API. For example, we know our data is on-prem and we want to launch a job on cloud. We call this API to copy the data before it launch the job there.
jobs you guys currently support on your cluster is most interact with some kind of object storage, or actually need another data storage you need to access, like data warehouse, tabular data warehouse, or something like that?
We basically use files as our input. So as long as like it sits in S3 or HDFS or the GCS, it's just a Parquet file.
So it's
Yeah.
like more like object storage.
Yeah, it's object storage. Yeah.
So your pods, once they do their work, either array data or training and stuff, generate some metrics, right? Do you actually put those metrics someplace and you have your own dashboard that can then use those metrics to see what happened during those jobs?
Yes.
Okay.
Yes, we integrate with some third-party vendor solution for the metrics.
Is that part of the blog, which
No.
Yeah, I think we are out of time, so we are.
Yeah,
but
I'm
but
happy to
yeah,
take more
yeah,
questions
yeah.
offline.
All right, thank you.